So we talked last time about how to find your feasible region based on the constraint provided, one or multiple constraints provided by a linear programming problem. Let's revise again the constraints that we had. So the constraints that we had, first we had x1 to be less or equal to 4 and 2x2 less or equal to 12, and we had 3x1 plus 2x2 to be less or equal to 18. So those are the constraints as shown on the graph on the right. We discussed in details how to find your needed feasible region by drawing linear lines representing those constraints. Now the next step, how to find your maximized or minimized equation through this region. So now you decided this is your feasible region. Okay, then I have a maximization problem. When I solved my linear programming problem, I had the maximization problem. In this case, we're assuming here just an example. So let's say we had, you need to maximize the z to equal 3x1 plus 5x2. And that equation is not represented on the graph. Now how I'm gonna maximize the final solution of my linear programming problem on the graph, and how does that help me through the graph? Firstly, we need to know that solving this kind of linear equation comes by trial and error, which means you start to plug in some numbers for z and draw it in your graph and see if that kind of line that you draw based on assumed value of z is maximizing or minimizing the feasible region. So when you say maximize z, that means maximize the area that this equation can cover from the feasible region that we see. So in the ideal world, you can say if your final solution was maximizing z to equal 3x1 plus 2x2, as we can see here, so you take the most out of your feasible region. It means that's your ultimate solution. But in this case, that's what we have. We have z to equal 3x1 plus 5x2. Now let's say the value of z is 10. So 10 equals 3x1 plus 5x2. How does that work? Well, if we do that, let's have a ruler in here. So if we do that, we'll be somewhere in here. So that's your z line. It will be somewhere there. So that would be 10 equals 3x1 plus 5x2. But we can say we still have too much area missing from the feasible region. So we need a higher number, or we need to change the z in order to have the best out of our feasible region. So we had a template graph down here that will give us a better representation. So again, this is our feasible region that we just discussed. Its exact copy graph of the previous one. We just have some space to write our numbers. So here, that's our first iteration or first assumption, to have z to be 10 equals to 3x1 plus 5x2. Okay, what if we said let the z equals to 20, that equals 3x1 plus 5x2. Well, if we draw that line, it will be this line in here, as we can see. So this is the line representing 3x1 plus 5x2 to equal 20. We are still missing almost half of our feasible region, so we need to try to go up. So we are trying to let our line be higher than that to cover as much of the feasible region as possible. So in this case, let's say z, you can say z equal 30, z equal 32, 35, but instead of doing the guessing game, so that's what we want. Like, as we can see, that's how the line pattern of 3x1 plus 5x2 is going, having 10 or 20. This is how it is going. So we can say the ultimate goal is to have a line passing through the tip of this shape in here. So in order to do that, you need to know what's this point. So you need to find the z that satisfies your equation to give you this line. So that's a basic mathematics basically. So if you can follow here, you can see that x1 equals 2 and x2 equals 6. So this point is point 2 and 6. That's x1 and x2. So now we had a z to equal 3x1 plus 5x2. So we have x1 and x2, but we are not sure how to achieve this line. So 3x1 plus 5x2, we can't change it, but we can change the z. How to know the value of z? Just plug in the value of x1 for that point and the value of x2. If we do that, we can maintain that z equals 3 multiplied by 2 plus 5 multiplied by 6. This equals 6 plus 30, which gives you z to equal to 36. Okay, that being said, so z, let it equal to 36. That equals the main equation, which is the maximization equation, which says 36 should equal 3x1 plus 5x2. If we do that, then we will get this line. So now we covered as much as we could from our feasible region that considered an acceptable graphical solution. So this equation belongs to this line. And that's it. Now you could decide graphically based on your starting with your constraints, then drawing your feasible region, and then decide what is the optimal point that give you a maximized z. What's the value of z that give you the most out of the feasible region that you decided.